Hello, this is going to be a quick derivation of the Clausius-Clapeyron equation that we use to determine saturation vapor pressure given a temperature, or we can use it to determine the vapor pressure given the dew point temperature. So a little bit of background. This is going to rely upon your knowledge of both specific entropy, as denoted by this equation here, ds equals dq over T, dq being heat added at a certain temperature, so an infinitesimally small amount of heat added at a specific temperature, and our relationship that we learned in lesson number 13, which is latent heat equals the heat added during a phase change. And we can't really measure the du per se, but we know that internal energy has to change so that we can make or break bonds in a phase change. And then we got the work due to expansion or contraction. So we need to account for that. As I previously stated, it gives us a relationship between saturation vapor pressure and temperature, or vapor pressure and dew point temperature. So for the purposes of this derivation, we're going to use L, which is the latent heat of a phase change. In this particular case, it's going to apply to latent heat of vaporization for the most part, but you could also make this apply to sublimation, since the alpha change in the phase differences is approximately the same. So let me just start by going down to step number 1. Step number 1 is really just expanding out the latent heat equation that we have up at the top, or as part of the background that you learned in lesson number 13, where you have the heat added equals change in internal energy plus work done. Note that because we were talking about water to vapor phase change, P equals E sub S for the phase change. And we can now come down and do the integrals and expand it out, and we end up with latent heat equals U2 minus U1 plus E sub S alpha 2 minus E sub S alpha 1. And we're going to denote that particular equation as number 1. Now we're going to move over to step 2. Now we're going to apply what we know to specific entropy. And we know that from this same equation over here that we started with, that L, or the latent heat of vaporization, also equals dq. It is the heat added for the phase change. Now we're just going to multiply that by 1 in the form of temperature over temperature. And what we end up with is latent heat equals T times dq over T. And from what we know of specific entropy and the equation that we previously discussed, that dq over T equals the change in specific entropy. This is from lesson number 9. So now we can move down here. We got latent heat of vaporization equals TdS. And we can expand that out, and we're going to end up using this a little bit later in step number 3, which we'll move on to right now, where we combine equation number 1 and number 2. And we can just simply say that they equal one another because they both equal L if you look back up here at step 1 and step 2. And then move all the ones, the state 1 variables, to the left-hand side and all the state 2 variables to the right. And what does this tell us? It tells us that we're going to define a new variable g, which is called Gibbs energy, equals the U plus E sub S alpha minus T times specific entropy at a certain state. And it is equal to the same at the second state. In other words, G is conserved, or G1 equals G2, between phase 1 and phase 2. And G we define as, or is defined as, Gibbs energy. G is conserved for a phase change at a constant temperature and pressure. But we can move on to step number 4 and differentiate G, because G is not constant with respect to temperature and pressure, so we can actually differentiate it. Notice how I said it is conserved for a phase change at a constant temperature and pressure. But as we do the derivation, as we expand it out, we see that we have dg equals du plus E sub S d alpha plus alpha d E sub S minus TdS minus S dt. what I have bracketed here is du plus E sub s d alpha. If you come back up here, here's du E sub s d alpha. This is dq, this is latent heat 1 to 2, or latent heat of vaporization. What we also know from over here in step number 2 is that latent heat also equals TdS. And we've got the TdS right here in the equation. But this equals TdS also. So this is where we have from steps 1 and 2, we've got latent heat equals du plus E sub s d alpha equals TdS. So this TdS minus this TdS, they cancel each other out. What you're left with is dg equals alpha dE sub s minus s dt. So from step number 3, we know that dg equals 0 for a phase change. It's conserved. In other words, g1 equals g2. So we can also say that dg1 equals dg2. So if we move down to the final step, which is 5, which is some rearranging of dg1 equals dg2, and here you've got dg1 on the left-hand side, you've got dg2, which is just applying this equation up here, down here to the specific states. We then multiply by 1 over dt, and we end up with this equation here. We can rearrange this equation and end up with dE sub s over dt equals s2 minus s1 over alpha 2 minus alpha 1. And this is already a step applied, which is multiply by 1 again, which is t over t. We've done something like this before. And we end up with t times ds equals over t d alpha. But TdS from step number 2, as well as we used it in step number 4, is equal to L. And this is L12, or the latent heat of vaporization, where phase 2 is vapor. So one thing we can say about the specific volume of vapor is that it's much, much greater than the specific volume of liquid or solid. So to a close approximation, we can say that alpha 2 plus alpha 1 is approximately equal to alpha 2. So we substitute alpha 2 in to the equation instead of using alpha 2 minus alpha 1. Then we will move on to the next step. We use the equation of state for water vapor. Since phase 2 is vapor, we knew that alpha 2 is specific heat, or specific gas constant for vapor times T over E sub s. We plug that into the equation and we end up with dE sub s dt equals the latent heat of vaporization times saturation vapor pressure over the specific gas constant for vapor over T squared. And we just run through the integrals at going from some reference value to E sub s, some reference T to T. Okay, sorry about the distraction, just had to go answer the phone. I think we were right about here. So now we just integrate from reference values to E sub s and t. And what we end up with is, you've had this integral many, many times. It's just ln E sub s over E sub s0 equals the two constants, which is latent heat of vaporization over specific gas constant for vapor. And this integral, 1 over t squared, or 1 over t squared, is the equivalent of this over here. So you've got minus 2 plus 1, minus 2 plus 1. And what that turns out to be is 1 over t0 minus 1 over t. And then we can take the exponent of both sides. We come over here, we've got E sub s over E sub s0 equals exponent, all that stuff. Now we can move E sub s0, multiply through. We got E sub s equals E sub s0 exponent latent heat of vaporization over specific gas constant for vapor, 1 over t0 minus 1 over t. This should look very familiar if you have used this before, the Clausius-Clapeyron. Now we just apply a reference point, which is the triple point of water, which from your previous lesson you know is E sub s0 is equal to 6.11 millibars and t0 is 273 K. That turns into the Clausius-Clapeyron equation, which is right here, which tells us that E sub s is a function of temperature only. And if we stick TD in here, this would give us E over here. That is pretty much the entire derivation. There are going to be pieces and parts of this on homework, and there may be a few pieces that I would expect you to know on a test. For instance, if I give you the general form here, which this is a form of the Clausius-Clapeyron, you should be able to take me down through here with the assumptions that alpha 2 is much, much greater than alpha 1, so it's approximately equal to alpha 2, and being able to step through the integrals and come to the Clausius-Clapeyron. The other thing you should be able to do is coming back up here towards the top is understand the relationship between specific entropy and latent heat and how you get to this particular form, the TDS, because we end up applying that a couple times throughout this derivation. That's pretty much it. Hopefully you'll ask some questions in class if you have them, and talk to you all soon.